Hi, I'm back again to talk a little bit more of a technical topic this time, specifically the challenges of miking ensembles. In my last video, I showed how having two microphones on, just by unmuting both of them, we got feedback much more quickly. Uh, this also explores some of the additional challenges of having two microphones on the same ensemble. Now, I'm not going to go through all the math that you see on the screen here, but it kind of forms the basis for what we're doing. You can see we have an ensemble here of 18 people, three rows of six, and if we were going to use two microphones following the 3-to-1 rule, they would be placed approximately like this: 2.6 feet in front of this person, 2.6 feet in front of this person, and that gives us roughly 7 feet to the furthest person. So you can see quite a range of distance there from the people. So that's a little bit of a challenge. But what this video focuses on more than anything is what happens to people who are close to both mics, but closer to one than the other. So specifically, you can see we have this person highlighted, and we're going to do the analysis on them. We could also do the same analysis on this person here as well beside them. So what you notice is that with our mics properly spaced, the challenge we have is that this person in highlighted in pink here is 3.58 feet from this microphone, and they're 6 feet from this microphone. And the challenge with that is both microphones are going to pick them up. And in fact, the difference in volume in those two microphones is only going to be about 4.5 decibels. And the distance in the feet is only 2.44 feet. So this is only 2.5 feet roughly further away than this one is. So it's pretty, everything is actually pretty close. And what's interesting is if we look at that difference in the mic distance, it becomes important because it's kind of relates to how the time delay, right? Sound takes time to travel. It's got to travel 2.44 feet further here. So that's going to result in a delay of so many milliseconds. And it is that delay that causes problems. If we look at that 2.44 feet, there's two things that we need to measure from it. One is, what is the full wavelength frequency of that? So if we were to look at one wavelength, and I'll show you diagrams here coming up, what would happen to that sound? Where is it a full wavelength, that difference in distance? And that's about 460 hertz. So 440A is the A just above middle C, so you kind of get an idea of what tone. We're definitely in the singing range here. The half wavelength frequency is also very important, and that's in that 2.44 feet, what would be 1/2 of a wavelength instead of a full wavelength, and that would be half of the full wavelength, or 230 hertz. And why does that mean? What's important about that? That means that at 460 hertz, even multiples of it will be reinforced. So 2 times it, 4 times it, 6 times, 8 times, etc. All of those multiples, the volume of those pitches is going to be made greater because the sound coming into this microphone and into this microphone are in phase. The sound is additive, so it gets louder when we have both microphones on. Seems like a good thing. However, look what happens at 230 hertz, and odd multiples of it, so times 3, times 5, times 7, etc., those signals will be out of phase and will be subtractive. Let's look at this. Here are some pictures that kind of help illustrate this, and we're going to listen to it as well. So this delay, you can see I have two waveforms. This one is kind of shifted to the right some amount of time, and the amount of time is equal to how long it would take it to travel 2.44 feet. So you can see at 460 hertz, if you look at this pink line, everything lines up perfectly. Everything's in phase. If I were to add this number to this number, I get a bigger number, not a smaller number. However, look at what happens at 230 hertz, or half a wavelength. So I've shifted it over the same amount in time, but it's only half of a wavelength. And so now you see here I've got a negative value. It's below the white line. Here I have a positive value above the white line. If I add those together, the result is less, right? They subtract. This one is actually subtracting from that one. And if we keep going and look at 690 hertz, which is 3 times 230, so 230 times 3, 690. Again, they're out of phase, subtractive. However, if we go up to uh, 920, and I can see I got a typo in my text here. At 920, it's 2 times 460, and even multiple 460. Everything is additive again. So some sounds will be made quieter, some sounds are going to be made louder. So let's switch over to our digital audio workstation here and take a listen to what that sounds like. So right now I've got everything muted. And what I'm going to do is, and I'm playing a time selection here. You can see this is where I got those waveform pictures from. So I'm just looping on a time here. So let's undo just 230 hertz. This is the half wavelength frequency, and we play it. The clicking there is because of the looping. You can try and ignore that. Now watch what happens when I bring on the second 230 hertz, which is slightly quieter than that, to represent turning on that other microphone. Notice how it got quieter. Also focus over here on these VU meters. I turn off this microphone. Notice the signal level is up. It's louder. I turn it on. It got quieter. So by having 2 microphones on, I'm actually getting a quieter signal at 230. Well, let's look at what happens at 460. Notice I got the signal there. Look at the signal level. Now I turn on my second microphone, and it got louder. So remember at 230, when I turned on the second microphone, it got quieter. Here at 460, it gets louder. And again, at 690, on multiple, it got quieter. And let's try one more at 920. It gets louder. So now let's just, these tones are all mathematically related. Let's turn on 460 and 690 and 920. Nice chord, right? Now let's look at what happens when I turn on the delay. So now that's with one microphone, right? So now I'm going to select all of these delay channels so I can turn them on and off at once. So we're going to have our nice chord playing. Now I'm going to turn on the other microphone. Turn it off. You can see quite a difference. Probably not what you were expecting at all. Let's try it with even the 230 on, and we'll go from there. And let me also select that delay channel as well. And now we unmute. Well, I don't want to bore you with listening to tones all day, but that's what happens when you have 2 microphones picking up the same sound. One of the things I want to show you at this level is with just these 2 tones. You'll notice the delay signal is slightly lower in volume. That represents that 4.5 dB difference because the microphone is further away. Well, hopefully that made sense to you, and we can, you can understand why it is that it's always better to get one microphone that can do the job reasonably well than 2 from a coverage standpoint. And in fact, I want to just jump up to one chart here that I did the math on. And this analyzes 3 different miking scenarios. One microphone near that ensemble of 18, one mic that's far away from them, and then using 2 mics placed using the 3-to-1 rule. Notice that the signal strength in the front from the one mic, so this is combined usable signal level that I can use into the mixer to amplify. With 2 mics, it's not that much greater than it is with one mic. It's basically only 2 dB difference. That's almost, you can't hear the difference. The front to back ratio, it's actually the 3-to-1 mic actually has a worse front to back ratio, meaning not by much, 1.2 dB, but it means I don't get as even a coverage. So it's marginally better for the front row volume, but as you just noticed, we get all of these interference problems from the sound coming from this person to this microphone and from this person to that microphone. That difference makes a huge difference in how that sound can be amplified. And I would just note that problem of even and odd harmonics all the way up through just continues all the way up through the audio spectrum. So the human voice singing a tone or a song, those, it's not just going to be a couple of frequencies which are affected. It's all of the complex frequencies that make up that singer's voice. And as you can imagine, someone male, if this was a man here and this was a lady here, remember I said this spot has the same problem, just the microphones are reversed. If this is a guy, he's going to be impacted one way. If this is a female, impacted a different way. Whereas these people back and through here, not impacted at all because they're much closer to this microphone than here. Again, there's a lot of math that went into this, and I will post this document along with this video. There will be a link to this PDF file where you can review this if you want. But it kind of shows the math that goes into all of this and the thinking behind it and why it is that in general, for small ensembles, and by small ensembles I'm meaning 18 or less roughly, that single microphone placement that we see kind of here, where we've got that microphone about 4 feet, 4.5 feet back. This is the best picture. By the way, this heart-shaped thing that you're seeing here in the circle, that's the microphone's pickup pattern. I won't explain all of that, but we want to stay within these lines here. That's kind of how I chose the distance back. The microphone is kind of where this Y and X axes intersect, so right here in the middle would be where the microphone is actually placed. That will conclude the video, and I hope you found this very helpful and informative.